Math 1314, Tyler Junior College, 6.5, Cramer's Rule, Video 5. What happens when the denominator is 0? In the setup for Cramer's Rule, and ever since we started this section, we kept saying as long as the denominator is not 0, as long as this isn't 0, as long as this isn't 0. Well, I'm not worried about what the formula was for the denominator and the setup for Cramer's Rule. Let's just encounter it in action and see what happens. For example, let's solve 3x plus 4y equals 5 and 6x plus 8y is equal to 7. Now, if you're paying close attention, you can tell that this is destined to crash. And here's why. Notice that if you just look on the left side of the equation, the second line is twice the first line. In other words, if I double 3x plus 4y, I get 6x plus 8y. However, on the right side, 7 is not double 5. When I double 5, I get 10, not 7. This is destined to have no solution because if I double the top equation, just by inspection, if I double the top equation, it becomes 6x plus 8y equals 10. Well, there's no way that 6x plus 8y can simultaneously be 10 and 7. So whatever makes one work will not make the other one work. So this is destined for no solution. But how does this wash out when we're finding a solution via Cramer's rule? Well, let's set it up and see. For the denominators, it's just the determinant of the coefficient matrix. In other words, the coefficients are 3, 4, 6, and 8. Let's go ahead and set up the numerators. And remember, when we set up the numerators, we replace the corresponding variables' coefficients with the constant terms. For the x numerator, we're going to replace the x's, which means we keep the y's. And for the y numerator, we replace the y's, which means we keep the x's. And then we just replace with the constant terms on the right side of the equal sign. In the x numerator, we replace the x's with 5 and 7, or I should say x coefficients. And for the y numerator, we replace the y's coefficients with 5 and 7. Now, at this point, I'm not going to go too slow to do the determinants calculations. I'll just talk them out, starting with the numerator of the x. And I will do some highlighting, just real quick highlighting. In the numerator of the x, we do 5 times 8, which is 40, minus 7 times 8, which is 28. 40, wrong color, 40 minus 28 is 12. Our first numerator becomes 12. Let me go ahead and do the numerator for the y as well. 3 times 7 is 21. 5 times 6 is 30. 21 minus 30 is negative 9. So everything's going swimmingly. But when we get to the denominator, 3 times 8 is 24. 4 times 6 is also 24. And 24 minus 24 is 0. So we'll get 0 on both. So what can I glean from this? Well, I'm going to glean a little bit more than you might think. If the denominators are 0, but the numerators aren't, then there is no solution. If the denominators are 0, but the numerators aren't, then there is no solution. So 0's on the bottom, but not on the top means no solution. But when we were solving a system of equations, there was also a possibility to get an infinite number of solutions, such as this system. These two equations are identical. You can tell because if you double the first one, it becomes the second one, which means any solution to the first is also a solution to the second and vice versa. Individually, either one would be a line, which has an infinite number of points. So there's an infinite number of solutions. But all that aside, let's say you don't observe any of that, and you just jump right into Cramer's rule. Let's see what would happen. Okay. For our denominators, we just take the coefficients, the determinant of the coefficient matrix. So 3, well, same as it was before. 3, 4, 6, 8. 3, 4, 6, 8. In the numerators, on the x numerator, we replace the x coefficients, which means the y coefficients stayed the same. And on the y numerator, we replace the y coefficients, which means the x coefficients stayed the same. And then we replace the other replacements with the constant terms, which are 5 and 10. Now let's figure out what happens. All right, modeling the multiplications again. First numerator, 5 times 8 is 40. 4 times 10 is also 40. 40 minus 40, of course, is 0. By the way, we already know the denominators are 0 because it's the same denominator as it was back here. On the y numerator, 3 times 10 is 30. 5 times 6 is also 30. 30 minus 30 is 0. And if you notice, in this case, not only we get 0 on the bottom, but we also got 0 on the top. I'm going to try to grab all this stuff and move it up a little bit. I missed the top 0, the 0 on the y, so that I can type the statement below. Similar to this statement here, in fact, I'm going to go into this statement, copy it, and spell numerator correctly. And then I'm going to insert that into this text box here. We'll need to widen it and modify it. If the denominators are 0 and the numerators are 0, and I'm pretty sure you can't have one 0 and not the other. I haven't verified that, but something about it tells me that can't happen. But if the denominators are 0 and the numerators are 0, then there's an infinite number of solutions. So 0 in the denominator is what triggers a non-traditional solution set. Normally, a system has a unique solution. A 2x2 system has a unique solution. The exceptions are when it has no solutions or an infinite number of solutions. 0 in the denominator sets off both of those exceptions. If 0's in the denominator but not the numerator, there's no solutions. But if 0's in both the numerators and the denominators, there's an infinite number of solutions. And just a reminder that when there's an infinite number of solutions, there is a way to describe them. Sometimes you're asked to describe what those infinite number of solutions are. Sometimes you're not. But on this assumption that we already concluded there's an infinite number of solutions, because these are the same equations, one way to describe them, and this is mentioned in a video back in 5.1, is to say it's the set, let's make that this, it's the set of ordered pairs x comma y such that, and that's what that vertical line reads as, and then you just have to write either equation, because if it satisfies one equation, it satisfies both because they're the same equation. I could have used the second one. So the solution is the set of all ordered pairs that make 3x plus 4y equal to 5. So in summary, when you get a 0 in the denominator, one of two things happens. Number one, the numerators aren't 0. In that case, there's no solution. Number two, the numerators are also 0, in which case there's an infinite number of solutions, which can be described as the set of all ordered pairs such that either of the equations is true.